Okay, so this video is looking at using unit vectors and Cartesian vectors to find resultant forces in 3 dimensions. Specifically, the example and then the group practice problem from lecture 2, slide 30 onwards. So I'll go through the first one. I'll give you a chance to pause the video, and then I'll talk you through the solution to the second one. So the first example is roughly sketched in the video now. If you want to, it might be easier to look at the PowerPoint at this point. Force 1 is only acting in the x-y plane, in the y-z plane. Force 2 is acting in all 3 directions. So if you imagine the x-y plane is like the surface of a table, force 2 is acting at 45 degrees beneath the table, so it's pointing downwards at 45 degrees from the bottom of the table, from the bottom of the surface. So force 1 relatively easy to solve. Force 2, we're going to have an extra step in there to the problems we've looked at before. So force 1, the Cartesian vector, will just be 4/5 of 500 j plus 3/5 of 500 k. No I component because it's not acting in the x direction. And what you can see in the diagram that's given in the PowerPoint in the lecture is grey shading to give you a better idea of which plane that force is acting in. Force 2 is acting in all 3 directions, so we're going to need an intermediary step. So the first thing we're going to do for the x and the y component is find a force 2 dash as well. So force 2 in the z direction is relatively easy. That's just going to be 800 sine 45. And force 2 dash, the red line on the diagram, bringing it up level to onto the xy plane. So if you imagine that arrow pointing beneath the surface is then being raised up, so how much of the force is acting along that surface? Well, that will be 800 cosine 45. So along that red line we've got 800 cosine 45. So force 2 in the x direction will simply be 800 cosine 45 cosine 30. And force 2 in the y direction will be 800 cosine 45 sine 30. If I then put those into my calculator, I can get force 2 as a Cartesian vector, putting my x, my y and my z together. So I'll get 489.9 I plus 282.8 j minus 565.7 k. And then I can resolve it as you'd expect, as I have before, which you have before. You just add your i's, add your j's and add your k's. So your resultant force for that example should equal 490 I plus 683 j minus 266 k. So if you want to pause the video at this point, the next part of lecture 2 gives you a group problem solving activity, and that starts the screw eye is subjected to 2 forces, F1 and F2. There is an extra step in that you have to find the magnitude of the resultant force and then the alpha, beta and gamma angles that we talked about in the introducing unit vectors video. So have a go, see if you can do that, and then if you push play I'll show you how to do it afterwards. Okay, so you should now have had a go at the group problem solving activity. So F1 is very similar to the previous example we just did. So I'll draw it and then I'll start talking about it. So that should be the question you're working on Rather badly drawn there, but I think you get the idea. So force 1 is like our force 2 from the previous question, so we're going to have to work with a force 1 dash along this red line in order to find our x and our y components. So F1z is going to equal minus, because it's acting downwards. And in fact, that's one thing I missed from my previous example. So if I go back, my z component should be negative. You probably picked that up a lot quicker than I did, because it's acting below the xy plane. Hence this minus down here at the bottom, and I realise you can't see where I'm pointing at the bottom of the screen. So that's where that came from. So minus 250 sine 35. F1 dash is then going to equal 250 cosine 35. F1x will then equal 250 cosine 35 to bring it onto the F1 dash line, and then sine 25. And F1y 250 cosine 35 cosine 25. And again, just as before, I can put all those into my calculator and get a Cartesian vector for F1, which will come out at 86.6 I plus 185.6 j minus 143.4 k. So that's F1. F2, slightly easier, but I haven't shown you how to do it yet. You may have picked it up already from the unit vector introduction. But F2, you can just take the magnitude of the force and multiply it by the cosine of the angles to the x, the y and the z axis. And if I work that through, I'm going to get minus 200i, and the minus comes because the cosine 120 is the 120 degrees is bigger than 90 degrees. And you can see from the diagram it should be negative because it's going in the negative x direction. So then if I add that to my F1 from the previous slide, from the previous screen, my resultant force will then come out at minus 113.4 I plus 468.4 j plus 56.6 k. And then if I use Pythagoras on that, so to find the magnitude, how big is that overall resultant force? My overall resultant force ends up being 485.2 newtons. However, that's not the end of this question. We've also asked for directions. So directions, you're going to need to remember this line and this bit for the next slide. So my alpha angle, my angle from the x-axis to the resultant force, is going to equal the inverse cosine of the x component of the resultant force vector, so minus 113.4, divided by the overall magnitude of the force, 485.2, which equals 103.5 degrees. And similarly, my beta, sorry I missed my inverse part there, will equal the inverse cosine of 468.4 over 485.2, which will equal 15.1 degrees. My gamma will equal the inverse cosine of 56.6 over 485.2, which is 83.3 degrees. And that answers the group problem solving activity, shows you how to use some of those unit vector ideas, particularly the alpha, beta and gamma angles, and helps you find the resultant forces and resultant vectors in 3 dimensions.